Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, today in this particular lecture, we will going to discuss about another instantaneous code generation mechanism, that is your Huffman coding. So these are the outlines. We're going to start up with the introduction. Then we're going to discuss about Huffman coding, which will be followed by the algorithm generation steps of your Huffman code. Then we're going to discuss two examples related to your Huffman coding, that is how we will going to formulate Huffman code. And finally, we're going to conclude by discussing some of the special points about your Huffman coding. So in our earlier lecture, we had already studied about your basics of information theory, what is average information content of a binary symmetric source, what is information rate, what is average information in the message, entropy, etc. So we have also taken a look about the fundamentals of source coding and discuss one of the variable length code generation method, which is your instantaneous code generation method, that is your Shannon-Fano. So now in this particular lecture, we are going to discuss about another method of variable code generation, that is your Huffman coding. So the code for each sequence is found by generating the Huffman code tree for the sequence. So here, in order to generate some instantaneous code with the help of Huffman algorithm, we have to make that tree. So the Huffman code tree is an unbalanced binary tree. I mean, it is not always possible that all the branches will going to have the equal number of sub branches. So now we're going to discuss about the Huffman code tree generation algorithm. That is how we will going to generate the Huffman code for a given discrete memoryless source. Obviously, the knowledge about the different symbols generated by a discrete memoryless source and associated probabilities, that is known to us. So the derivation of the Huffman code tree is shown below. That is what we have to do in our first step. Have the n symbols ordered according to the non-increasing values of their probabilities, or you could say your decreasing probabilities. That is, out of the n symbols that would have been generated by your discrete memoryless source, then we have to order them in the decreasing values of their probabilities. So in this step 2, what we have to do is, then we have to group the last two symbols, that is the last two terms in that particular order. We have to group them together and form an equivalent symbol with the probability will be equal to p of n minus 1 plus p of n. That is, we need to add up the probabilities of all those two symbols, or you could say those two sub symbols, and form a equivalent symbol. So in our third step, we have to repeat step 1 and 2 until the only one symbol is left. So we have to keep continue these procedures till the time we will only going to left with one symbol. So now step 4, looking at the tree originated by the above steps, associated the binary symbols 0 and 1 to each pair of branches at each intermediate node. The code word for each symbol can be read as the binary sequence found when starting at the root of the tree and reaching the terminal leaf node associated with that symbol. So this particular fourth point basically tells us that how we will going to form the actual code. That is, we just simply had to put the binary symbols 0 and 1, and we have to move back and we have to obtain the actual Huffman code. So how we will going to do it? Let us understand it with a simple example so that the whole procedure or all the 4 steps would have been clear to us. That is how we will going to create the Huffman code for a given discrete memoryless source. So this is your example. We'll be given a discrete memoryless source which will basically going to generate these symbols, that is your m1, m2, m3, m4, m5 and m6, and the associated probabilities also given to us. That is, for generating m1 symbol the probability is 0.3, for generating m2 symbol the probability is 0.25, for generating m3 symbol the probability is 0.15, for generating symbol m4 the associated probability is your 0.12. Similarly, for m5 it is your 0.10, and for m6 it is your 0.08. So in our first step, we have to arrange those symbols in the descending order of their probabilities. So here in this particular problem, the probabilities given to us, they are already arranged in the decreasing order. That is, the probability of m1 is 0.30, which is greater than or equal to m2, and similarly it is greater than or equal to m3, it is greater than or equal to m4, and M5 it is greater than your M6. So these probabilities are already arranged. So this is our first step. Then what we have to do is we have to group the last two symbols, that is your M5 and M6, and we have to add them these two probabilities, that is your 0.10 and 0.08, and we have to make a single symbol whose probabilities will be the summation of these two, that is your 0.10 and 0.08. So the probability that we obtain is your via adding these two, that is your 0.18. And when we again going to analyze all these probabilities, so in this particular hierarchy or in your this S1 step, that 0.18 probability as per your hierarchy, or you could say decreasing order of probability, it comes at the third place. Rest of all the things will going to remain same, that is 0.30, 0.25, then 0.18, that is greater than 0.15 and 0.12. So we have again maintained a hierarchical list for that. Then in the next step, what again we have to do is we again have to add up the last two symbols probability and arrange them in another column. So again we have to take up these last two symbols, that is 0.15 and 0.12. The probability, equivalent probability of this composite symbol turns out to be 0.27, and again we have arranged in this particular column like this one. So 0.30 and 0.27 is greater than 0.25, so we have put this value 0.27 in between 0.30 and 0.25, and again last one is your 0.18. And then again we have to again follow the same procedure, that is we again have to add up these last two probabilities or least two probabilities in this particular column. So what we are left with is your, we again have to, by adding this 0.25 and 0.18, we'll have obtained 0.43, which is greater than 0.30. So this in this particular column we have maintained this 0.43, then again 0.30 and again 0.27. Then again we have to perform the same operation, that is we have to add up the least two probabilities. So the summation of 0.30 and 0.27 turns out to be 0.57, which is greater than 0.43. So we have made this particular column, that is your 0.57 and 0.43. So we have completed this particular process till the time we will going to obtain a single symbol. So in the next step, if we're going to add up the 0.57 and 0.43, we're going to obtain this 1. So this is your second last step, or you could say this is your last step, just because we have to start numbering from this particular step only. So in this particular table, what we have this this is your message symbols, that is the discrete memory source, the different symbols that it is going to generate. Again these are 6 symbols and these are your associated probabilities. Then how we will going to obtain that code, so that we need to understand. As we have studied in our step 4, that we have to give certain bit to the top branch of the tree. That is, we can say that for 0.57 we have assigned this symbol 0, and 0.43 we have assigned this symbol 1. This we can change also, that is for higher value of probability we can assign 1, and for lower value of probability we have assigned 0. So but the point is we have to follow the same assumption. So as of now I'm considering that for higher value of probability I'm assigning this 0, and for lower value of probability I'm assigning 1. Obviously I'm talking about these two probabilities only. From where we have actually obtained this 0.57, it is basically the summation of these two symbols, that is in your step 3. So again the code associated with your 0.57, that is your 0. So the same prefix thing would have been applied here also, that is we have put this value 0, 0 as a prefix, and for higher value of probability, that is your 0.3, we have assigned this 0, and for lower value of probability, that is your 0.27, we have assigned this 1. The code associated with your 0.27 turns out to be 01, and for 03 we have this 00, and for 0.43 we have this 1. So this particular thing would have been clear to you. So now next again we have to travel backward, and from where we have got this probability 0.43, it is basically the summation of these twos, that is your 0.25 and 0.18. So again 0.43, the code associated with that 0.43, that is your 1. So this would have been used for your prefix purpose. So again we have used this prefix 1 1, and for higher value of probability we have assigned this 0, and for lower value of probability we have assigned this 1. So we have also obtained the code associated with this probability 0.18, that is your 1 1, for 0.25 that is your 1 0, 0.27 it is your 0 1, and 0.30 that is your 0 0. So again moving backward, so where we have got this 0.27 probability, it is the summation of these two things. So again the code associated with your 0.27 is your 0 1. So we have assigned this prefix 0 1 0 1 in both of the cases, and for higher value of probability, that is your 0.15, we have assigned this 0, and for lower value of probability, that is your 0.12, we have assigned this probability 1. So the code associated with this particular probability, that turns out to be 0 1 1, and for 0.15 it is your 0 1 0, and again for 0.18 it is your 1 1, 0.25 it is your 1 0, and 0.30 it is your 0 0. So again we have to moving back, and we need to find out that from where we have got this probability 0.18. It is basically the summation of these two probabilities, that is 0.10 and 0.08. So the code associated with this 0.18, that is your 1 1. So we have used this 1 1 as your prefix, that shown here, 1 1 and 1 1. So the higher value of probability we have assigned this code 0, and for lower value of probability we have assigned this code 1. So if we closely observe this particular column, we can easily demarcate that we have basically obtained code associated with your symbol M1, that is your 0 0, for symbol M2 it is your 1 0, for symbol M3 it is your 0 1 0, for message symbol M4 we have 0 1 1, M5 we have 1 1 0, and for M6 we have 1 1 1. These are your distinct instantaneous codes. So this is how we will going to form the Huffman code for a discrete memoryless source. So whatever we have formulated, the entropy h of x of the given source can be evaluated as minus pi log of pi. So when we use the probabilities that has been given in our last problem, we have evaluated this minus summation pi log pi. We have evaluated this as your 2.36. You can check it out. That is for P1, that is your 0.30, P2 is your 0.25, P3 is your 0.15, P4 is your 0.12, P5 is your 0.10, and P6 is your 0.08. So by evaluating minus pi log pi summation, we have obtained this 2.36 bits per symbol. This is the entropy or average information of our discrete memoryless source. And when we're going to obtain the average length code of the encoding vector, that is, I'm talking about these are the code vectors. When we will going to find out the average code vector length L bar, that turns out to be summation p of xi ni, where ni is the number of bits used to encode a particular symbol and p of xi is the corresponding probability. Then we got what we got is L bar turns out to be 2.38 bits per symbol. So here we can say that the average code word length is greater than your entropy. So efficiency would have been evaluated as h of x over L bar, that turns out to be 99%. So we can say that there is a very small amount of redundancy associated with it, and that is equivalent to 0.02 bits per symbol. So here in this particular case, Huffman coding will going to provide us the 99% of the efficiency. So Huffman coding relies on the fact that both the transmitter and the receiver know the sequence set, that is prior knowledge is there, that is both the transmitter as well as the receiver will going to have those coded sequences before communicating, and they can build up the code table so that they can easily communicate with each other. So now we're going to discuss another example. So obviously I'm not going to give you the complete procedure that how we will going to obtain that Huffman code. Specifically I will try to give you a hint how to solve that particular problem. So here in this particular example, we have considered the same problem that we have already discussed in our previous class, where we have discussed about the binary symmetric source, and we are basically trying to get the weather forecast, and we have taken the 3 consecutive dates weather forecast, that whether it is sunny or cloudy. So on 3 different dates the weather will be your all 3 days, that is your sunny sunny sunny, the probability associated with your 0.729. For sunny and third day is cloudy, that is your 0.081, and similarly all 3 days the weather will be cloudy, that probability is very low and that is equal to 0.001. These code words are not your prefix free codes, these are your only distinct codes that we had already discussed in our earlier lecture. Now we will going to find out that how we will going to generate your Huffman code for this discrete memory disk source, which will going to generate this 8 symbols and whose probability associated with them is this one only. If you closely observe that they are already arranged in the descending order of the probability. So we have arranged them in the decreasing order of the probability, that is your 0.729, 0.081. These are already given in your decreasing order of the probabilities, and these are the associated symbols. That is, all 3 days sunny, the associated probability is 0.729. For sunny and cloudy, the probability is your 0.081, and similarly for all 3 days there will be a cloud or cloudy weather, that probability is your 0.001. So again we have to form that coding tree, and how we're going to do is we just have to add up these least two probabilities, that is your 0.009 and 0.001. When we're going to add up, we're going to get this 0.010. So when we're going to order them in the column, then the position of this composite symbol of these two will be at your 5th position. Again we have to continue this particular process, that in the next time we have to add these least two probabilities, which is your 0.018, which is greater than your 0.010. So we have to put this here. So again the addition of these two turns out to be 0.028, and when we have compare with the above probabilities, its position would have been there. Then in the next step, when you're going to add up these last two probabilities, the valuation turns out to be 0.019. And similarly, when we will going to add up these two least probability values, that value turns out to be 0.162. And when again we're going to add up these least two probabilities, we're going to obtain this your 0.271, and this is your 0.729. So here this 0.729 will always be on the top, just because the summation of any two least probabilities will never greater than this 0.729. So this is how we will going to obtain that your Huffman coding tree. In this particular thing, we have obtained all 3 steps. Now the last step is evaluating the code words associated with the distinguished symbols. So this particular figure is basically showing our step 4, that how with the help of this coding tree we are going to obtain the individual codes. So initially for this your SSS, here we are saying that for higher value of probability we are giving the symbol 1, and for lower value of probability we are assigning that symbol 0. So these branches will basically showing us that particular branch is made up of which two particular of sub branches. This is the meaning of your coding tree, or you could say your tree. So this 0 we would have been obtained via the summation of these two sub symbols, and again this particular sub symbol would have been obtained via adding these two symbols, that is your SSC and SCS. So again the high value of probability we have given this 1, and for low value of probability we have given this 0. So now in the similar manner, this particular sub branch would have been made with the help of this CCS and this complete sub branch. So for high value of probability we have given this 1, and for low value of probability we have given this 0. Then again this particular sub branch would have been formed with the help of these two sub branches, that is summation of this as well as this. For high value of probability we have given this sub branch value as your 1, and for low value of probability we have given this sub branch value 0. And similarly this particular sub branch would have been formed with the help of these two symbols, and similarly this particular sub branch would have been formed with the help of these two symbols, that is your SCC and your CCC. So now the question arises that how we will going to formulate the code via having this particular tree, how we will going to obtain the code associated with your different symbols. So if you closely observe this particular tree, this is the topmost branch and symbol is your SSS. So the code associated with your SSS, that is equal to 1. Similarly, when you have to evaluate the code associated with this particular symbol, that is your SSC, so we just have to start from the top, that from where it has been originated. So it would have been originated with this your 0, or you could, in simpler word you could say that how we will going to reach this particular symbol SSC via traveling through this particular tree. So first we have branch of this 0, then this one branch, and then one branch. So this is how we will going to reach your symbol SSC. So the code associated with your SSC is your 011, that is your this 011. It has been written over here. And how are you going to obtain this particular second symbol, that is your SCS? So right, starting from the top, that is 0, again 1 and 0. So this is the code for your SCS 010. And similarly, how we will going to reach this your CSS from the top, right, starting from the top, that is your 0, this particular branch is also 0, and then again 1. So the code associated with your CSS is your 011. And similarly, how we will going to reach this CCS, that is starting from the top, 0 0 0 1 1. So this is the code with your CCS. And similarly for your CSC, 0 0 0 1 0. This is the code for your CSC. And for your SCC, how we will going to reach this your SCC from the top branch, that is your 0 0 0 0 and then 1. So this is the code for your SCC. And what will be the code for your CCC or cloudy in all 3 days? This particular symbol, that is 0 0 0 0 0. So this is the code for your CCC. So this is how we would generate the Huffman code tree of given information source. The whole process we had actually discussed. The Huffman coding achieves the lowest possible expected code word length. You could say it is the best code and it will going to get the lowest possible expected code word length in comparison to your Shannon-Fano coding. So it is better code, you could say. Whereas your Shannon-Fano code was your suboptimal code. But the example we have discussed in our Shannon-Fano coding, so in that particular case, it has given us 100% efficiency just because the probability distribution is of the type of 2 to the power minus nk. But in general, Huffman coding performs better. So it is also one of the most used method for instantaneous code generation methods used in your source coding. So hopefully you all have get the insight about your Huffman coding, that how we will going to obtain Huffman code tree and how we will going to generate the Huffman codes when a discrete memoryless source is given to us. So in case of any doubt, you can ask me in the comment section. I'll try to solve them out as soon as possible. So these are the references. Thank you very much for your patient hearing.